Hi there. Today we'll look at Grokking Generalization Beyond Overfitting on Small Algorithmic Datasets by Alethea Power, Yuri Burda, Harry Edwards, Igor Babushkin, and Vedant Misra of OpenAI. On a high level, this paper presents a phenomenon that the researchers call grokking, where a neural network will generalize all of a sudden after weigh the point of overfitting on a dataset. So you train the network, it completely overfits on a dataset. Training loss is down, training accuracy is 100%, but it doesn't generalize at all to the validation set. And then when you continue training the network, at some point it will just snap into generalizing on these data sets that they're researching to a 100% generalization, so 100% accuracy on the validation set. And this is extremely interesting. And as you can see, the paper has been presented at a workshop at iClair 2021, which means that it is not yet, it's sort of work in progress. So there is still a lot of unclear things about this phenomenon. It's as I understand it, a phenomenological paper that just presents, look, here is something interesting that we found. And I think it's pretty cool. So we'll dive into the paper. We'll look at this phenomenon. They do dig into it a little bit, into what's happening here and try to come up with some explanation. So the basic premise of grokking is the graph you see on the left right here. Now, it is a little bit pixelish, but I hope you can still see what's happening. The red part is the training accuracy. And on the x-axis, you have number of optimization steps, and this is a log scale. So that's important to see. This is a log scale for training steps in this direction. Now, the training accuracy, naturally, after a few steps, it shoots up to 100%. We'll get to what data sets these things are in a second, but it's important to see the network can, in fact, fit the training data extremely well, and it just overfits. However, the validation accuracy, if you can see it, there is a little bump here, but then it goes down again almost. I don't know whether we should even regard this as a little bump that's actually happening. However, it just stays down, and then after, you can see orders of magnitude more steps. This is 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth steps. It shoots up and it starts to generalize as well. This is very interesting because, this essentially means you keep on training for a long time, and when all hope is lost, still the network at some point will generalize. Now, why is this happening? And as I understand it, it's not the case often that the network drops down again out of generalization, though I haven't actually seen this investigated, like if they run for 10 to the I don't know how many steps. But it seems like once the network is generalizing, has training accuracy of 100%, it doesn't fall out of that again. So the question is, how does this happen? Like what's happening here? Why is this happening? Why is it all of a sudden, and what makes it work? And for that, it's a bit important to understand a very related phenomenon, in fact, a connected probably phenomenon called the double descent phenomenon in deep learning. The double descent phenomenon graph looks somewhat similar in that the premise is that on the x-axis you have the number of parameters in a network. So the number of parameters in a neural network, and then on the y-axis you have, let's say, loss. Okay. Or actually, let's say accuracy. I'm not sure. Loss. Most of these plots for the double descent phenomenon are actually loss. So if you consider the training loss, as you increase the number of parameters in your neural network, you will fit the data better and better, the training data. So you get a curve that goes something like this, and then it just stays at 0, right? So there's 0 training loss as you increase the number of parameters. These every point on this line is a neural network with a given number of parameters that has just been optimized to convergence. Okay, that's important to remember. On the left here, we saw a graph during optimization. On the right here is a graph of many different networks, all of which have been trained to convergence. Now, what you see with the validation loss in this case, so if you look at the validation loss, it might, at some point, it might come down with the training loss, right? And then in the classic fashion of machine learning, as the number of parameters go up, you start to sort of overfit. The validation loss goes up again because you start overfitting, you start memorizing the training data set. And then at a point where pretty much the number of parameters equal the number of training data points, like the number of, let's just call this n, then you have, again, like a really crappy validation loss because you're just remembering the training data. However, if you increase your parameters beyond that point, so if you scale up your neural networks even more, the validation loss will come down again and actually end up at a lower point than if you were on this place over here, if you had not enough parameters. So there is a point beyond overfitting where you have more parameters than data points. And interestingly, for neural networks, it is the case that it happens that they can achieve generalization, in fact, better generalization with overparametrization than comparable underparameterized models, which flies in the face of all statistics and whatnot, but we know this phenomenon exists. Okay, so we knew that things like this can happen, like the training loss can be perfect and still we can have generalization, right? The Grokking phenomenon is a phenomenon where I'm gonna guess the creators of the double descent phenomenon haven't looked quite as far in order to, I guess they simply ran training to convergence for a number of steps and then they looked at the validation loss. So I guess they would have stopped somewhere in between here, between 10 to the third and 10 to the fourth steps. This research here is simply what happens if we let it run for a really long time. Then this shoots up as well. And it seems like for a lot of conditions you can do this. So now it's worth looking at what kind of data sets we are interested in here. The data sets are synthetic data sets in this paper. The synthetic data sets are binary operation tables. So here the data sets we consider are binary operation tables of the form A, and then here this is like some sort of a binary operation. A, let's just call it multiplied, A multiplied by B equals C, where A, B, and C are discrete symbols with no internal structure, and the circle is a binary operation. Examples of binary operations include addition, composition of permutations, bivariate polynomials, and many, many more. In fact, they have some examples, I think, down here. So here you see some examples like addition and multiplication, but also more complicated things like a polynomial that you then do modulo a prime number, division modulo a prime number, and so on. So the way you create a data set is you construct a table. And in the table you have a number of these symbols. And then you define binary operations by simply filling in that table. Okay? So if this were, I don't know, like A plus B, and A and B are numbers, then right, A plus B is C. If A is 1, B is 2, C is 3, and so on. But you can define this as many different things. A lot of the experiments in this paper are of the group S5, which is the group of all permutations of 5 elements, which I think has so this is a group with 120 elements. So your table would here be 120 by 120. And the operation would be the sort of composition of permutation. So every permutation of 5 elements composed with another permutation gives you yet another permutation of 5 elements. So you can just construct this table. And then what you do is you just simply cross out a few things in the table. So you say, okay, here I'm just going to cross out a few things, and this is what the network should predict, right? I'm going to train the network on the data that I have, and I'm going to predict the cells that I crossed out. This way you can exactly measure how good the network is, right? There is no noise effectively in the data. It's all very well defined, and a human goes about this with, I guess, with sort of a logical mind. They try to figure out like, what's the rule? What's the rule? A neural network can simply remember the training data, but then it will not generalize to the hidden fields because it cannot memorize those. So if a neural network generalizes here, it also kind of means that it must have somehow learned the rule. And this is pretty interesting. So there are a number of quantities to keep in mind. The 3 quantities are, first of all, what's the operation? Because there are more and less complicated things for these networks to learn just from the kind of difficulty, the complexity of the operation itself. Second of all is the dataset size, or the size of the binary table itself. In this case, it's 120 by 120. And the third one is how many things are left away. So how large is the training data fraction, the fraction of the table that is filled in for the network to learn? All of these 3 things are going to play a crucial role in this Grokking phenomenon and when and how it appears. For example, here you see they have trained neural networks on this S5 group, right? The permutations of groups of 5 elements, until they reach generalization. So they simply run it and they measure how long does it take a network to reach 99% validation accuracy or higher, right? That's the thing on the left is essentially, the answer would be something like between 10 to the 5 and 10 to the 6, right? Okay, so, and they measure this as a function of, you might not be able to read this, but it says training data fraction. Okay, how much of the training data is filled in? And you can pretty clearly see, if I just give it like here 20% of training data, there are even some runs that do not generalize in this number of steps. Now, would they generalize if you were to optimize for even longer? Who knows, honestly. But you can see that as soon as you give like 30% of the training data, the runs in general do generalize, but they take something like 10 to the 5 number of steps to do so. And then as you increase the training data fraction, this snap to the generalization happens faster and faster. You can see right here, as you give more training data, it goes faster and faster until it generalizes. And the generalization happens, as I understand it, fairly like quickly. Like it doesn't generalize because it remembers the training data. And this always happens, as I understand it, in a fairly similar number of steps. But then at some later point, it just kind of snaps and completely generalizes to the validation set. And this is really interesting. So we know that the more training data we have around, the better, right? That's one recognition. Then the other thing is they try to figure out, okay, which parts of the optimization algorithm are making this Grokking phenomenon happen. And here they figure out that weight decay, in fact, is one of the big drivers of this. So if they add weight decay to the algorithm, and they try a lot of different things. They try full batch versus mini batch, with dropout, without dropout, modulating the learning rate, and so on. But weight decay seems to be one of the biggest contributors to this Grokking phenomenon, to the fact, or to how fast these networks generalize. You can see that the network generalizes much sooner if you have weight decay turned up than not. Also, they make the observation that if you have symmetric operations, if your binary operation is symmetric, then also the Grokking phenomenon happens much faster than if you have like non-symmetric operations. This might just be a function of these networks, which if you have like something like a transformer, it's sort of kind of invariant to the symmetry. So it might, like, essentially one data point is sort of 2 data points in disguise if it's symmetric, or there's only half as much stuff to learn. You choose whatever you want to interpret this as. But I think this is not as important as the weight decay. And why do I highlight this? I highlight this because, also down here you can see they analyze the results of a network that has learned to generalize like this. So on the right, you see a t-SNE projection of the output layer weights from a network trained on modular addition. So this is x plus y modulo 8, I think. The lines show the result of adding 8 to each element. The colors show the residue of each element modulo 8. So if you do the t-SNE projection, you can see, the lines are obviously drawn by the authors, but you can see there are structures where if you go along the line right here, they've colored, essentially this is always adding 8, adding 8, adding 8. So there are structures where the rule for generating the data is clearly present in the data itself. In the network's weights. This gives you a strong indication that the network has not only just remembered the data somehow, but has in fact discovered the rule behind the data. And we have never incentivized the networks to learn these rules. That's the wild point. There are architectures where you try to specifically tell the network, look, there is a rule behind this. I want you to figure out the rule. You can maybe do symbolic regression, or I don't know, like you can try to build an internal graph and reason over it. No. We just train neural networks right here. And it turns out that these networks can learn these rules. So why do I relate this to the double descent phenomenon? In the double descent phenomenon, it is assumed, or I've heard the authors of these papers speak about their kind of hypothesis why this happens, and this is a bit mixed with my hypothesis as well. They speak of, for example, weight decay being one possible explanation. So they say, if I have a bunch of data points, let's say I have a bunch of data points right here, right, and I want to do regression on them. Well, if I just do linear regression, I have one line, right? It's fairly robust, right? It's fairly flat, it's fairly robust because it's just one parameter. Now, if I start to add parameters, right, I get to a point where I have a good number of parameters, this polynomial, maybe kind of like this, still fairly robust, right? You can see how it might generalize to new data. Then, right, so the blue one would be somewhere here. The dark blue one would be somewhere here, where the validation loss actually goes down with the training loss. But then when I keep adding data points, parameters, then, classically I'll start, my overfitting right here, and it will not generalize to any point that might be in between, like one here or so. Error will just go up. So the green would correspond to the point where I just start to interpolate the training data. But then what happens if I go on, if I make even higher order polynomials or higher order neural networks? Well, at that point, at least these authors argue, do I have another color? This one. They argue that you get like a polynomial that, or a curve that, yes, it has a lot of parameters, but it uses these parameters such that it can be sort of smoothly interpolate the training data. This curve is quite complicated in terms of the number of numbers you need to describe it, but it uses the fact that it has a lot of freedom. it can choose to be however it wants as long as it interpolates the training data, right? Yet it chooses to be smooth because of a combination of SGD, training it, and of weight decay. So the weight decay would prevent any of these numbers from getting too big and therefore getting like super out of whack curve. So the weight decay would in fact smoothen the curve, and that makes the model generalize really well because the smoothness now is reasonably generalizes to training data points that are in between. Like this data point is still fairly well represented by the purple curve. In fact, it's better than the dark blue curve in this particular case. So you can see that the authors here argue that weight decay might be an important contributor to why overparametrized networks generalize. And it's interesting that these Grokking, the authors of the Grokking Phenomenon paper here find the same thing. They say, okay, if we use weight decay, the grokking appears to happen much faster. Is this, I don't know what exactly they call grokking. I'm just going to call grokking this whenever the validation loss snaps all of a sudden from 0 to 100 on these data sets. Now, again, these are algorithmic data sets, so we don't know what happens. I think they do make experiments when they noise some of the data. So they have some noise in there, and I think they find that if they add noise, then it's way more difficult. I'm not sure though. Maybe I'm confusing papers here. But what might be happening right here, right? It's interesting because what might be happening is that by imposing this smoothness and the overparameterization, we're sort of biasing these networks to find like simple solutions, right? So if I have just very few training data points, if most of the cells here are blacked out, right, the simplest solution is simply to remember the training data. However, as I get more and more training data points, right, that give me more and more information about a potential underlying rule, it becomes simpler for me to understand the underlying rule than to remember the training data. It's more difficult to remember the training data than simply to learn the rule. So what might be happening here is that as I train, and this is always training here, the training happens always on the same data, right? You simply sample the same things over and over again, train on it. I think what might be happening is that you kind of jump around in your optimization procedure. You can see there's some bumps in the training accuracy here. So you kind of jump around. That's a song, no? So you jump around a bit, and in your loss landscape, there might be many of these local minima where you, in fact, remember the training data perfectly. So you kind of jump around a bit between them, right? You remember the training data perfectly, and then one of them is just you remember the training data as well. Well, now you remember the training data as well. However, the solution is just so much simpler that you stay there. This is not a good way of visualizing it. So it must be something like, here are the minima where this is the training, just the loss on the data. However, there is another loss, and that's the loss on, like for example, the weight decay loss. And the weight decay loss is, it's pretty good, all of these things, but then for one of them, it's just like, whew, because that solution is so much simpler. So you're going to jump around between those minima, jump around until, once you reach this one, this loss right here that comes on top of this is just so much lower that you're gonna stay there. And it's like, wow, I found such an easy solution. I'm not going to go out again. So, yeah. Now, the big question is, of course, how and why does something like SGD plus weight decay plus potential other drivers of smoothness in these models, how and why do they correspond to simplicity of solutions, right? Because simplicity of solutions is something that kind of we humans have built in, like, okay, what's the rule behind this? What's the rule? It's essentially assuming that there is a simple rule, trying to find it because it would make our life much easier. It's a simple explanation for what's happening. The interesting part is that weight decay, or something similar, something that's happening in these neural networks, is essentially doing the same thing, even though we don't tell it to do it. So understanding this, I think, is going to be quite an important task for the near future. And also, maybe we're not exactly right with the weight decay. Maybe there is some other constraint that we can impose that encourages simple solutions in the way we care about simplicity even more. And once we have that, it's like, this age-old argument: do these things actually understand anything? Well, in this case, I'm sorry, but if you have found this solution with the rule essentially built into the networks into the weights of the neural network, you can say, well, the network has in fact learned the rule behind this binary operations. So, who are we to say these networks don't understand anything at that point? And also, it gives us the opportunity to train these networks, and then from the structures of their latent spaces, we might in fact parse out the rules of data we don't know yet. So we let the networks fit, and we parse the underlying, maybe physical laws, maybe social phenomena. We parse them out from the underlying data. Oh yeah, here. Okay, there is an appendix where they list binary operations they have tried out, models, optimizations. So yeah, they use a transformer with 2 layers, 4 attention heads. So it's not a big thing, and also the data sets aren't super complicated, but it's pretty cool to see this phenomenon. Now again, if we have real world data, bigger networks, noisy data, it's not going to happen as drastically. And also they say, as you increase the size of the data set, where is that? As you increase the size of the data set, then this phenomenon is harder and harder. So if the entire data set is bigger, the Grokking phenomenon, I guess it's more tough to see. And also here is the experiment I mentioned, where you have several outliers, so noisy data points, and as you so this is the fraction of correctly labeled data points. So as you increase the number of correctly labeled data points, you can see the grokking happens in more often, or to a better validation accuracy than not. So, well, you can, I don't know if you can read this, but yeah, these down here, they have too many outliers. So with too many outliers, either the validation accuracy just stays at 0, or it just turns up like quite late. Okay, that's it. Here is an example of one of these binary operation tables that is a little bit larger. I don't know if it's one of the 120 sized ones, but this is something that would be presented to the network, and they say what? We invite the reader to guess which operation is represented here. Well, have fun, dear reader. Yeah. All right, so this was it from me for the Grokking paper. As I said, this seems like it's work in progress. I think it's pretty cool work in progress. It raises a lot of questions, and I think it's pretty cool. I wonder how this happened. Like how did people find this? They just forget to turn off their computer, and in the morning they came back and they're like, whoopsie doopsie, generalized. Though if you build these kinds of data sets, I guess you have something in mind already. Yeah, in any case, that was it from me. Tell me what you think is going on in neural networks, or is there like a super easy Occam's razor explanation that I'm missing? I don't know. Tell me what you think. I'll see you next time. Bye-bye.